Welcome to The Random Sample, a podcast from Maxis, the Australian Research Council's Centre of Excellence for the Mathematical Analysis of Cellular Systems. I'm Matt Coffey. In this podcast, we share stories about mathematics, statistics, and data science, and the people involved in these sciences. Our host for this episode is Dr. Tom Kimpson, a postdoctoral research fellow with Maxis at the University of Melbourne.
Thanks, everybody. Welcome to the Random Sample podcast. Today, we're going to be talking about an algorithm that most people have never heard of, but is maybe one of the most consequential algorithms in the modern world. That's the Kalman filter. And to talk us through this, we have two experts on the Kalman filter who spent decades working on this. We have Professor Rob Evans and Professor Bill Moran, both from the University of Melbourne. So Rob, Bill, great to have you here. Thanks for coming. So we're going to talk about the Kalman filter, but first I want to get a bit of a sense of like what got you guys into this, a bit of like your background, a bit of your origin story. So I'm going to start with you, Rob. So you did an engineering degree in Melbourne, is that right? And then you were working in the Air Force.
Yes.
So you want to sort of talk a little bit about that and how you got into mathematics, engineering, signal analysis?
Yep. So in the mid-60s, I did an undergraduate degree in engineering here. And I also, my degree had a lot of mathematics in 4 years of mathematics as well as a lot of engineering. And I had a scholarship with the Air Force for part of that. And then I had a bond and worked with the Air Force for a period of time. But I ended up at Newcastle University and did a master's there and then a PhD there, Newcastle in Australia. And at that time, a guy called Brian Anderson had finished his PhD at Stanford and come back, and he was made a professor like at 25 years old. He'd come back. And Kalman was at Stanford during that period. So he was heavily immersed in the culture of what Kalman was doing and others. And so it was a young, exciting department, and he brought people from MIT and a lot from the US all over the place. And it was a most unusual thing. And so it was really exciting to be there, and I did my PhD there. But my PhD was about quite mathematical optimization theory. But of course, we all did lots of stuff on Kalman filtering and all of, modern state space control theory and lots of signal processing. So
Yeah, that's so interesting. And Bill, same question. You've got much more like maybe a pure maths background, is that fair to say?
Yeah, so I came from the UK, as my accent suggests. Yes. And I spent my first 25 years, maybe 20 to 25 years in pure mathematics with no thought of any applications. And then some people started asking me questions in signal processing, and some people from the defense labs and around. And I found that, the mathematics I knew was useful in answering those questions. And so I got into studying signal processing, and it was interesting to realize that, the pure mathematics that I've been working on actually was useful. and there's an amazing power in seeing that mathematics can answer questions in the real world. It came as a surprise to a pure mathematician.
Sure, but quite reassuring.
Yeah.
And then you both had these like long careers, but when do you sort of both get together and form this sort of duo? I sort of know you as Bill and Rob together. At one point you were Bill and Rob separately.
Yes, most people see us as joined now. Well, after I did my PhD, I went to MIT and then Cambridge, and I came back and worked at Newcastle Uni. And then in the late 80s, Adelaide put forward a proposal for a cooperative research centre with people around the country, and I got involved with that, and Bill was a key player in that. So we met in around about 1990, and we've been working closely ever since for the last 35 years.
On and off. I mean, he's been off running big centres and things, but and we seem to be able to talk to each other and kind of what's the right word? Motivate each other and inspire each other, so it works.
Yeah. And a key part of our collaboration, I think, is we're both able to be completely honest with each other. And if I differentiate something on the whiteboard, Bill says, you should have learned calculus properly, Rob. Yeah. So we and I tell him the same thing about the Kalman filter. Bill, it works like this. So
the Kalman filter is very interesting. I mean, Rob will get into details in a minute, but in the early 90s, I was still neophyte in signal processing, and I came here from Adelaide. I was in Adelaide at the time, and I said to Rob, "What's this thing called the Kalman filter, Rob?" And I'd read some things, and they're full of these horribly long equations about what it does. And he said, "It's trivial, Bill," and he gave me a 2-minute explanation. I understood it perfectly after that.
Well, that's a perfect segue, I think. No pressure, Rob. But if you were to explain the Kalman filter, maybe just like, you're at a barbecue or something, you want to explain to someone to get like an intuition of what's going on, could you give us a 2-minute run through?
What sort of barbecue would want to talk about the Kalman filter, Tom?
all my barbecues are like that.
So, look, very briefly, though, the Kalman filter comes out of the tradition of Gauss and least squares. And I'll get to a little simple Noddy's guide to the Kalman filter in a sec. But there's quite a long history of Legendre, Gauss, Laplace doing least squares fitting. And this was a really significant thing when they tried to fit a model to measurements that had errors on them. And Gauss sort of worked out a way of doing that recursively. So doing a least squares fit. And everyone knows about a least squares fit. You all learn about a least squares fit of a straight line, and you find where it crosses one axis and what slope it is, and you simply minimize all the errors, right? And it turns out that you can do that recursively. So if you consider an average, taking the average of a number, you measure something that's constant, and you want to compute the average, you just add up all the measurements and divide by n, right? Well, that minimizes the least squares fit of a constant to that data. And if you imagine that you've done n measurements, and now you've got the average already, x bar n, and you take one more measurement, well, surely you don't have to resolve all the n+1 equations now. And sure enough, you don't, because you just add a bit. And the bit you add is the current mean plus 1 on n+1 times the measurement minus the old mean. And that's almost the Kalman filter.
Sure.
So you just do it recursively, and Gauss knew how to do that, and Laplace and all these people. So in around the time of the Second World War, Kolmogorov started looking at problems where you try and estimate the average. It's not quite the average of something that is randomly varying.
Yes.
So instead of a constant that you're measuring now, it's actually randomly varying, and that's got a mean and a variance. And he produced a set of equations for solving that problem. And to solve it, you look at the expected value of the least squares error. So you still do the least squares error, but you have to do expected values of it. And unless you know the probability distributions of things, you can't do it. You have to assume that you're going to linearly process the measurements. So you get something called the linear minimum mean square error estimate. So at the same time, Wiener in the United States produced a frequency domain version of this thing called the Wiener filter. And then through the 50s, several people started looking at recursive solutions to this thing. And the recursive solution that was most impressive is the Kalman filter. And it's impressive because it really allowed people to look at systems that were quite complicated, like described by a set of differential equations and a complicated set of measurements, not just measuring from one value, but measurements related to what you're interested in, and then allowed you to recursively compute the best estimate of the state of those differential equations. So It's linear minimum mean square error estimation that Kolmogorov had done, that Wiener had done. It's in the time domain, and several economists had also produced an answer to this. One of them was a guy called John Muth, who worked with Herbert Simon, who had a Nobel Prize and a Turing Medal. And so he produced a scalar version of it. But Kalman's version was very neat, and it really caught on because it made it so easy to apply. And people started applying it and started to forget where it came from actually.
Yeah, I mean, we'll definitely get into the applications. So just give like the listener maybe some more intuition. Have you got like a worked example maybe of like, how you're sort of combining this prediction idea with like updating based on some measurements and observations?
So let me explain it by Bayes' rule, because that's a nice explanation. There's an explanation that's not Bayes' rule. It's minimum mean square error, just like the averaging example. So the averaging example will tell you the intuition is you take the best estimate now of this varying thing is your best prediction of it to next time, plus again times the error between the measurement you took next time and your best prediction of what that measurement would be. So it's a predictor corrector, right?
So physically, this could be a boat out at sea, for example. You have some prediction of where you think the boat is going,
precisely,
based on your knowledge of the boats, and
yes.
you might have some measurement based on a radar measurement or something.
Yes.
Star measurement.
Yes, and that's exactly right, Tom. And so you just say, I take where I predict the boat's going to be, and I take a noisy measurement of where I now think it is, and I look at the difference between the predicted measurement and what my sensor said where it is, and I multiply it by a gain, and you add that to your predicted measurement, and that's the new estimate. And the gain is the ratio of the uncertainty in the noise in the predicted measurement and the uncertainty in the measurement you took. So that's how it works. But
under the assumptions, and there are some fairly rigid assumptions, it is the optimum way to do things. Yeah. There is no better way.
And those assumptions are that if everything's Gaussian and linear, then it's the best predictor in a probabilistic sense. And if those assumptions don't hold, it's the best linear predictor.
And so this idea of optimality is very interesting. I think that might come on to some things we can talk about later, like the wide application of the Kalman filter, which I guess is kind of grounded in this optimality of the minimization. Before we get onto that, I've heard that when it first was published, the Kalman filter in the 60s, it took a lot of time to catch on. It was kind of met with some skepticism. Is that true?
It is, because what happened is the engineers, which are electrical engineers mostly, they figured this sort of was known, but it wasn't known exactly in that form, but they thought the idea was like in the ideas that were around. Like
a Wiener filter or something?
No, like even doing recursive. So Peter Swirling had published a version of it, and John Muth in economics, and people had published versions of it, but they weren't in the same form as Kalman's. So, but for the electrical engineers, they said, yes, okay, yeah, it's recursive linear mean square error filtering. We know how to do that, although we haven't seen it in the form you've got. So he couldn't get it published in Electrical Engineering Journal, which he was electrical engineer. So it ended up being published in a mechanical engineering journal. But he persisted, and people started to find it was very easy to use, and the formulation he had used, and very powerful in terms of results. Can I tell you the Bayesian version of it?
Please do, yes.
Okay, so the Bayes rule, it's invented by Reverend Bayes in the UK in 1763, published after he died by his friend Richard Price. Bayes was trying to invert probability. Direct probabilities around by Laplace, but he was trying to invert. So what he was trying to do is say, if you have a hypothesis and you have some data, what's the probability of that hypothesis given the data? People knew how to do the probability of the data given a hypothesis. So the hypothesis, that we're all sitting in this little caravan recording, that's the hypothesis, and the data is we're all sitting in this caravan recording. But the other way around is much harder, inverting. So people were interested in things like what's the probability of God given that the sun rises every day and stuff like this. So they had to invert the probability. And what Bayes showed is if you in order to do that, you have to make the hypothesis random, and you have to have a prior probability on the hypothesis. So Bayes' rule then says the probability of a hypothesis given some data is the probability that you would see that data, given the hypothesis were true, times the prior probability the hypothesis is true. And it's normalized. This was sort of a bit of a shock to people because it meant you have to have, okay, what's the probability there's a God or something? So but it's a very powerful rule. So the Kalman filter actually implements Bayes' rule. And the way it does it is it uses another rule, and it's called the Chapman-Kolmogorov rule. But all it is that if you have the boat that you talked about before, and you project forward with a probability of where it will be if we keep going and the waves are moving it and that, and you have project it forward and you have a Gaussian distribution, it's going to be this mean with a variance on a Gaussian distribution going forward. Then you make a measurement of where you are, and if that measurement has got Gaussian errors, well, then you use Bayes' rule, because where you projected it was going to be, that Gaussian is the prior of a hypothesis, and the measurement you took is the likelihood, the probability that you would have seen that data if you were there. So Bayes' rule says you multiply these things together and normalize it, and that's exactly what the Kalman filter does. Exactly. So it just keeps doing it. So then you get your posterior from Bayes' rule, and that's your new prior. Now you go again. So you project forward based on that prior. Where's the boat going to be next time? And you work that out by standard means, and you get another measurement, and you just keep doing it. And that's the Kalman filter. Exactly the Kalman filter.
I see. And then if we want to go from boats to rockets, so the Apollo mission was one of the big flagship successes of the Kalman filter. Could you talk us through that a little bit? Like, how was the Kalman filter actually used there in practice?
Yes, so they were simply trying to keep track of the trajectory of the Apollo going to the moon. And so that's exactly the same as the boat one. So the computing was very minimal that they could have. So that's what was so attractive about the recursive solution.
So there's a nice completion of the circle here, because Gauss's original work was to compute the orbits of the asteroid series after somebody had published measurements of it. And Gauss didn't have a computer, even the minimal one that they had he did it by hand. And so he invented least squares. This was where least squares started with Gauss 200 and something years ago.
1805 or something.
Yeah. To solve this problem, the problem of finding the orbit of the asteroid series from data that astronomers have published. After he'd done that, a short while later, somebody else published data for another asteroid. He saw the publication. Within an hour, he'd worked out the orbit by hand.
And he was using recursive least squares. So it was very close to a Kalman filter, which is sort of fascinating. So the idea of least squares implemented recursively because of computational limits was really attractive to people. So on the Apollo, that was the reason it was a nice formulation that Kalman had done, and they had multiple different sensor measurements, and they wanted to know position and speed and everything of the rocket as going forward. So they just immediate implementation of the Kalman filter. So think of the Bayesian example that we gave. The Bayes interpretation is very clear in that case. They had projected the rocket forward from what they knew. Very simple calculation from Newtonian dynamics, and then they took a measurement on a sensor, which were noisy, multiple. They multiplied them together, Bayes' rule. They got a new posterior where they probably are, and that became the prior for the next step. And they just can iterate it on a very simple computer.
Yeah, and you don't need a lot of computation to do this. This is the key point.
Yes.
Yeah. Fantastic. And then, so these are sort of some classical examples from the 60s. Like in the modern day, do we have some examples? I've heard self-driving cars. I've heard of being using the Kalman filter.
Look, I think they're everywhere. I mean, air traffic control is a good example because all the aircraft are tracked by Kalman filters.
There are, because it has a relatively rigid set of assumptions, and people have tried to soften those assumptions and invented variants of the Kalman filter that handle more cases than the original one does. So it really, I mean, everywhere these things happen all the time. So
can you give us some intuition for why that is? So we kind of met each other working on the Kalman filter in gravitational wave astrophysics, which seems very different from radar tracking. It seems very different even from like, a boat on the sea or a rocket tracking these kind of problems. What is it about the Kalman filter that lets us use it in so many different areas of science and engineering?
Well, it's a mechanism for doing predictions on a time series that's got random, that's all. And so there's some random element in the time series. The randomness could come from, perturbations to the trajectory from unknown things, and it comes from the measurements you make too. So you have a trajectory that's got some equations that control where it's going, but you're not 100% certain. There may be unknown accelerations or bumps or different things, just like in the sea. And then you make noisy measurements on it. So you're trying to predict the best you can a random time series from the system from noisy measurements of that time series. You're trying to predict where it's going to be next all the time. And so it's just straight linear filter that does minimum mean square error prediction, Kalman filter. Does that make sense?
Makes sense to me. We've talked like a lot about the Kalman filter. I kind of want to get a sense a bit more of like both yourselves, your careers. You've had these long, illustrious careers across many fields. And we kind of heard at the start how you worked on all sorts of different things. And we've any advice to our listeners who might be sort of just starting out now on their own research career, their own research trajectory. What makes a good research career? How do you keep moving between fields in this way? What's the secret to long-term success?
So I had a co-worker whom you know, Sophia, who used to have on the bottom of her emails, Confucius: if you love what you do, you will never work another day. But it wasn't Confucius. We checked it out before we came, and it was Mark Twain who said this. But it's a good motto to have. Yeah, I mean, it's been an amazing time. I've just enjoyed having a career where you actually really enjoy what you do. Is magic, really. Yeah.
Yeah, and it's for me, I did a lot of, because of my engineering training. I actually, in the 80s, after I came back from postdocs, I did a lot of work with engineering companies, implementing things. So I was doing a lot of writing code in assembler and building systems and doing electronics and doing controllers for these big antennas. But I just found that I've always been interested in philosophy. I've been interested in mathematics, physics, everything. And so this privilege to have a life where you can work in all those things and keep going. I'm nearly 80, Bill's over 80, and we are still working like crazy, supervising students in different things, in new things, quantum mechanics, and all over signal processing and parts of mathematics. And we're even writing a philosophy paper now with a French philosopher on creativity. So all these things, I don't know, Bill said to me just recently, all this stuff is keeping us young. We're interacting with smart people who have new ideas, and we find we can contribute a lot and help, and we also learn an awful lot. Yeah. And also for me, I find, and I think for Bill too, that things you thought you knew, you keep learning them in different ways better and better. And it's especially true for a lot of mathematical things where I understand it now. And then 3 months later, I understand it now. And it's exciting and lovely, and working with lots of PhD students. And yeah, and you know the culture, Tom, in the physics group we had. It's exciting, and it keeps you alive, and it's a privilege, and it's wonderful.
Yeah.
So
I mean, there have been changes in academia. It's not. I think academia in our era was the best, right? And nowadays there are pressures, much more pressures, to publish a lot and to get funding and these sorts of things. Which was, I mean, we had to do that to some extent, but there wasn't the level of pressure there is now, I think, in academics. So
Yeah, sure.
we had the best times.
Well, I'm very jealous. Although I feel like I'm having a pretty good time myself.
Yeah.
And then, so it sounds like you guys have worked across a lot of domains. I think it may be surprising to some people to say, like, this guy's just a mathematician, this guy's just a signal analysis guy. What's he doing writing a French philosophy paper? What's he doing messing around with
that
That'll be impressive, yeah.
We'll leave it to our French colleague will do that for us.
But what's he doing in philosophy? What's he doing in astrophysics?
Yeah.
How do you think about that ability to sort of learn new things, jump between domains, apply universal principles to different areas?
Well, I mean, I'll say something, and then no doubt Bill will say something. But I guess what we find is that learning to look at a problem, break it down, and skills in a few fundamental things, and particularly in mathematics and statistics. So spending time, and we both do this, spend a lot of time understanding a problem, formulating it, like a lot of time formulating the problem until we really feel like we understand the problem. And I forget, was it Einstein or somebody said, if you spend enough time formulating the problem, the answer just drops out. And it's sort of true. So it doesn't matter, in a sense, what the domain is. If you struggle away and formulate the problem, even if it was in chemistry or something, you try and understand. And I don't know, human beings seem to have the ability to go into other, and with a lot of experience, to go into other areas fairly easily. You might not, as you get older, be able to be so creative in all other areas, but you can go into them and understand things. And it's surprising how much commonality there is between disciplines, to be quite honest. So,
I mean, mathematical training, I think, is second to none. And having that training and having, good lecturers when I was young who taught me these things, I think it allows you to move around more than perhaps other disciplines do. I find it relatively in inverted commas easy to read papers in other disciplines, quantum mechanics, for example, compared to people who come from other disciplines, I think.
Sure.
So I think the mathematical training is the place to be. And I went there because it was the most challenging.
Sure. Yeah. And then the famous engineer, I would call him, Richard Hamming, who I'm sure you guys have read a lot of, his famous book, The Art of Doing Science and Engineering. He has this discussion or this anecdote in the end about asking people what's the most important question in their field and why aren't you working on it. He's got this famous injunction called the Hamming question. Do you think about this when you're doing research? Do you think, like, what are the biggest questions I could solve? Or are you more people who sort of potter along and just say, that sounds quite interesting, let me see where I go with that?
I think, well, that looks an interesting question, and I think I have something to contribute. And by the way, breadth is another thing. Having, and Rob is amazing in this respect. I mean, having this breadth of areas gives you more power to tackle a given problem, because you can pull in tools from lots of.
Yeah. But I actually, I'm very interested in the sort of philosophical side of things too. And so things like when you're working with probability and statistics, you can easily decide that nobody understands probability very well. Everyone's already decided that nobody understands quantum mechanics. So looking at some of those problems, and trying to understand what do they really mean is a sort of a philosophical dimension to it that that really keeps you. You're not trying to solve a great problem, but you're trying to understand what does this stuff really mean. And it's true for probability. There's books and books on interpretations of probability. So when people are using the Kalman filter, for instance, and thinking about probability, of saying it's giving a probability distribution in a particular problem, it's worth asking what sort of probability are we talking about here? And a lot of great probability theorists, Cox and these people in Lindley in the UK, have, they're great mathematicians, but they also spend a lot of time trying to understand that philosophical side of particularly probability. So that's not answering a great question, but it's challenging yourself to understand what you're doing.
Sure.
A lot of what we do, to be fair, comes out of probability and statistics. And tools invented by people in those areas are really important for what we do. It's, you can hear it in what Rob says.
Sure. Yeah. Okay, I think we're sadly out of time, but thanks so much for a really interesting conversation, Rob and Bill, and thanks everyone for listening to the Random Sample podcast.
Thank you very much.
Thank you.
Thank you.
The Random Sample is a podcast from Maxis, the Australian Research Council's Centre of Excellence for the Mathematical Analysis of Cellular Systems. We are also proud to have the support of these partner organisations: the Australian Data Science Network, the Australian Mathematical Society, the Statistical Society of Australia, the Optima ARC Training Centre, the Matrix Mathematical Research Institute, and the ARC Centre of Excellence for Mathematical and Statistical Frontiers, which created the podcast. You can find the Random Sample on LinkedIn, Blue Sky, and X, formerly Twitter. Our email is hello@therandomsample.com.au. Make sure you're following us wherever you get your podcasts. Leave us a rating or a review, because we think stories about maths, stats, and data science are worth sharing, and we want others to find out about them as well. I'm Matt Coffey. Thanks again for listening to The Random Sample.